So let me start by welcoming all of you to the first seminar in a new seminar series that we decided to start at the School of Computer Science. It's called the Pearls of Computation. So let me start by sort of explaining to you what the idea behind this seminar series is, and to give you an idea of what season 1 of the seminar series will be like. Because like with Lost, we are going to have season 2, 3, 4, 5. So that there is going to be a never-ending series of Pearls of Computations. Just because there are just so many things to tell you, and there are so many key figures in computer science that we might want to learn about. Okay, we live in an era of specialization. Each one of us works in a possibly different field, subfield of computer science, and we tend to focus and rightly so, in order to survive in an academic environment, we tend to focus on the things that we work on. However, even I think in the fields that we work on, there are lots of things that belong to the history or prehistory, if you wish, of our subject that we might not be aware of. So the purpose of this seminar series is just to present a bird's eye view of the work of several key figures in computer science. And to begin with, we're going to focus on the people who have received the ultimate accolade in our field, namely the ACM Turing Award, which is sort of the Nobel Prize for computer science. And try to explain to our audience, as well as to ourselves, what is it that these people have done? How did they get to their discoveries? Why the discoveries are so important? And what kind of legacy they've left? And also, in between, it might be also interesting to have a look at some of their personal life stories and how the stories that they have lived, the stories that made their lives, actually shaped the way they thought. So in this semester, we are going to have 5 lectures, apart from today's one. Eyjolfur is going to tell us about the work of Dijkstra. Kristin is going to tell us about the work of, well, sort of someone, and he will tell us later on what it is when the time comes. Henning is going to tell us about Donald Knuth. Pure Thor is going to talk about COD and the relational model. Today, I'm going to focus on Robin Milner, this gentleman that you see here on the slide. The book cover that you see on next to him is a Festschrift volume that was produced when Milner turned 60 in '94. And that book is called Proof, Language, and Interaction, and I've shamelessly stolen, as a subtitle for the talk, the title of this book. Now, let me run a little poll. How many of you have heard of Milner, had heard of Milner before now? Okay, so several people who have either attended my talks or our courses. So it's not 100%. Now, these are some of the honors that he has received during his lifetime for his work. And I say selected honors because he has received more. Okay, he was a British, he received the British Computer Society Technical Award. He was a distinguished fellow of the British Computer Society. He was a fellow of the Royal Society. In the UK, that's a really big thing. As I said, he received the ACM Turing Award in '91. He became a fellow of the ACM in '94. He received an award which is close to my heart because it's the Career Award of the European Association for Theoretical Computer Science, of which I'm now president, for good or for worse. He was also a foreign associate of the National Academy of Engineering, stress engineering. So the American Association is fairly enlightened. You can actually get be inducted in their National Academy of Engineering for doing computer science work. This might probably never happen in Iceland, but you never know. You never know. So how do you come to get all these awards? And these are just selected. He got more. He was a fellow of the Royal Society of Edinburgh. You name it. He was a founding member of the European Academy of Sciences. This is just, well, the top of the iceberg. How do you come to receive so many awards? Well, let me have a little intermezzo. Today we live in an era in which every scientist and the output and the impact of every scientist is measured. Bibliometrics is a big keyword. If you look Robin Milner up, you go to the DBLP, which is sort of an archive of many publications. It indexes quite a bit. He has 100 entries spanning a period of 40 years. That's 2.5 entries, unless I'm mistaken, per year. It's not a huge output. There are several people at Reykjavik University who actually have more publications, more entries in the DBLP than Milner does. Now, his H-index, that's another key measure today, was 43. That's good, but there are people in computer science who have H-index over 100. Did they do more than he did? Well, probably not. Probably not. But if you look up at some of the impact that this work has had, and now following bibliometrics, I'll just show you some of the citations. These are his top 6 most cited pieces of work. Note, 4 of them are books. And if you take the first one, it's cited more than 9,000 times. If you sum up the citations of the first 2 books, I don't think I would be mistaken in saying that that's more than the whole computer science department at Reykjavik University. And these are his just top 2 citations. So this may mean something. Whatever he did, it certainly had impact. And in the small, I can tell you it certainly had impact on my work and on the work of my wife. Now, let me continue on this line. Today, you will find that there is a Royal Society Milner Award. The special interest group of the ACM on programming languages is just establishing a Robin Milner Young Researcher Award. There's been a Milner Symposium. And every year at the University of Edinburgh, where Milner had his most creative period of his life, he was there from 73 until sometime in the year 2000, there are Milner lectures every year. And these Milner lectures sort of are given by really top-class scientists that somehow embody his ideal of people who do work which is theoretical, but with strong applications in practice, strongly applicable theoretical research. And I hope that I will convince you that this is part of the philosophy of the man as he was developing his work. Now, what has he done? Well, if we look at the Turing Award citation, now this dates to 1991, when he was 57, when he received the award. He didn't stop there, he continued. But already in 1991, the award citation lists 3 distinct and complete achievements. I will tell you, hopefully, I will try to convince you what this award committee actually meant by complete. And even if they were distinct, you will see later on, I hope, that there is a red thread that links all these developments. The first thing is about something called LCF, which was probably the first theoretically based yet practical tool for machine-assisted proof construction. The second was ML, the first programming language to include polymorphic type inference, and I will try to explain later on what that means, and a type-safe exception handling mechanism. And then CCS, which is the bit I know best because that's really my area of work. It's a general theory of concurrency, of parallel processing. Now, what does it all mean? Why should I bother about these 3 complete and distinct achievements? How did Milner actually get to these discoveries, to these achievements? And what was his research philosophy? I've already mentioned a little bit about it, but I think sort of we could learn from him, certainly, about a way of conducting research. We will not reach, probably most of us will not reach the depths and the levels at which he pushed his research, but we can all be inspired, even as students. Now, let me give you the one-pill version of what I'm going to tell you later on. Okay, so Gordon Plotkin, in a talk that I will mention right at the end of the talk, said that Robin Milner was a craftsman of tools for the mind. That's a big thing. But what did he mean by that? Well, my summary, my sort of explanation is that Milner developed extremely elegant, theoretically founded, very well-founded abstractions, which turned out to be very useful. Now, abstractions are very fundamental in computer science. We don't want to deal with all the nitty-gritty phenomena that are running inside our machines. We must find the right abstractions to comprehend the complexity of the software, of the computing systems, of the hardware that we actually build. Milner had an incredible knack for finding the right abstractions. Solutions to be as simple as possible, but no simpler. Occam's razor. Always look for the simplest possible explanation. And he found them in very many cases. This is a quote from Mats Tofte, who used to be a graduate student of Milner, and now he's the vice chancellor at Reykjavik University in Copenhagen. Robin Milner was a scientist who thought really big, but he could take his visions and bring them, compile them all the way down to theorems. He was a visionary, but he could get his hands really, really dirty and prove complicated theorems and build complicated systems. So he could span the whole spectrum from coming up with the big ideas to actually making them work. Here's another quotation from Robert Harper, one of the major researchers in programming language theory. He says, what impresses me most of Robin's contribution to programming languages was not just the impact, we've seen the impact, but also the idea that the ideas that he had seemed to come fully formed. They were like Venus, who just comes out of the waves of the Greek sea. Of course, he had thought for long and hard for years about these things, but when the things actually came out, the abstractions came out, they were just right. That's a skill. That's a gift. Now, let me tell you how we actually came up with these ideas by sort of trying to follow the path of his intellectual development and the story of his life. I'll try to pepper the presentation with quotes from Milner himself. There is a very good interview by Martin Berger on the web that I encourage you to read if you're interested. Now, Robin Milner was the son of an army officer. He was born in Plymouth in the UK, but his family was not really an affluent family. He was a very smart kid, but he was not affluent. Still, he ended up at Eton School, Eton College. Now, the name might ring a bell. I mean, he could simply not afford to be there, but he was there as a scholar, which means he was recognized as a very smart kid, so they gave him a scholarship. In his own words, what he learned to do there was to spend all nights working on math problems. He was good at maths, and he learned to work really, really hard. Now, I mean, if you're in the UK, the path from Eton to Cambridge is a natural one, and that's where he went, and he studied for a bachelor in mathematics, which he completed in '56. He then actually went on to philosophy. So he took part 2 of the moral sciences curriculum, which meant mostly he was doing philosophy, and he finished it in 1957. Now, his first experience with computer science was not a very rewarding one. He took a course on programming the EDSAC. The EDSAC is that machine that was, at least, that machine that you could see there on the slide. It was one of the first computers, really general-purpose computer that worked. It was designed by Maurice Wilkes at Cambridge, and they were given courses on how to program that machine. Milner was underwhelmed. He didn't think the programming was elegant at all. It's just everything looked very, very arbitrary. You just write one instruction after the other, and this didn't inspire him at all. So in fact, he said, I decided that I would never get near a computer again in my life. Well, you know, whenever you say something in your life, then later on things turn out to be different, isn't it? And you will see that for Milner, this happened at least a couple of times. So at this point, he left Cambridge. He was actually encouraged to stay, probably for his PhD, we will never know. In fact, he never had a PhD. But he was an old school. At that time in the UK, you could have a pretty good career in academia as well without having a PhD. But he felt really tired of academic things. So he went to work. His first job was as a math teacher at Marylebone Grammar School. And he did it for about sort of one year, 2 years. Then, remember, he said, I will never get close to a computer again. So his first real job in industry was with a computer manufacturer, of course. Where else? So he worked for Ferranti for 3 years. Now, Ferranti, for those who don't know, were the company that produced the first commercial computer. That's the Mark I. It's the one that this lady is programming over here. Note, a lady. At that time, programmers were mostly women. Then somehow this good tradition disappeared in many countries, but hopefully it's coming back. So what did he do? He made sure that the machines they were actually they were selling were actually working. And he also wrote his first compiler. At that point, he thought, okay, maybe I should get a job in academia, isn't it? A couple of years before, he was tired of academia, he wanted to get into the real world, then having experienced the real world and working for Ferranti, he said, well, maybe I should get back, which is what he did. Despite not having a PhD, it was not a problem at all at that time to find a job in academia, and he went to the City University. Now, the City University at that time was a bit like Reykjavik University in the early days. Their job was to train people to do certain jobs. It was not like a research university of the modern day. Now, when he was working for the City University, in his own words, he had a kind of double life. During the day, he was teaching math to engineers, which he didn't think was particularly challenging or extremely rewarding in a way. But he started getting interested in research. He started getting interested in artificial intelligence, for instance, at least as far as topics having to do with machine-assisted theorem proving were concerned, logic. Now, in the early days of artificial intelligence, sort of building theorem-proving machines was one of the key things. John McCarthy in Stanford had a group working on that, and John McCarthy is another guy whom we might hear about in this seminar series because he also received the Turing Award and is considered to be one of the key influential initial figures in artificial intelligence. He started getting interested in logic because of the theorem proving stuff. And in fact, he was interested also in relational algebra. There you had a language which was essentially a logic that you could use to describe queries, data queries. SQL is nothing but first-order language with a lot of sugar on it, but operating on finite relational structures. However, even someone as smart as Robin Milner didn't make very much progress on that topic. So there's another lesson. Even the big guns, they have the moments, they have the times when they actually don't succeed at the things they want to do. As you will notice, Milner is someone who always liked to challenge himself. So he had a pretty cozy lecturer position, but intellectually that was not rewarding enough. So what did he do? He took up a research position. So he went from what was possibly a permanent position at the City University to a temporary research position in Swansea, at the University of Swansea in David Cooper's group. Now, David Cooper was one of the early guys who was working on decision procedures for logical systems. So it's sort of his interest really matched Robin Milner's initial interests in logic. Now, in Swansea, Robin Milner wrote an automatic theorem prover for himself, just as a leisure activity. That was not part of his job description. Now, what is an automatic theorem prover? Now, a theorem prover is a computing device, a piece of software, if you wish, that given a description of a logical system, which you may think of sort of some rules of inference that allow you to prove new theorems from old theorems, sort of, and given as input something that you want to prove, we'll try to actually prove it. Now, if you're talking about an automatic theorem prover, the machine will do all the work by itself. Remember, people are interested in artificial intelligence, and proving theorem is one of the things that we humans believe exhibits intelligence in some form. So if you really want an intelligent system,
it should automatically prove the theorem by itself if the theorem is true. You don't want human intervention. Otherwise, it's sort of a combined effort, man-machine. One of the things that Milner said straight away was that he was shattered by how difficult automatic theorem proving was. How little you could do by purely automated means at the time. At the same time, Milner started developing an interest in program verification. And in a way, that's probably not so surprising. If you build a theorem prover, you want to trust the results of the proving process that the machine actually does by itself. Otherwise, how can you believe the theorems that the machine tells you are true? You have to verify that the machine is actually doing the right steps. It's not proving false things from true ones. Proving true things from false ones, that's easy. Everybody can do it. And in fact, it's a valid rule of inference. So that's why sort of the two interests actually go hand in hand. And he also started working on the idea of simulation. And he wrote a very influential paper called An Algebraic Definition of Simulation Between Programs that is still cited after 1971. In fact, we still cite it in our work whenever we mention the word simulation. And again, you may think, remember he studied philosophy, so he was always interested also in philosophical ideas. He said, okay, simulation is a philosophically interesting concept. Why? Because you have something abstract which is a representation of a concrete phenomenon. Now, how can we be sure that this abstract representation of the concrete phenomenon is in any way faithful? To do so, you need to establish some kind of relation between the two, between the abstract world and the concrete world. And this simulation, this notion of simulation, is a way of establishing this relation. At that time, also let me introduce some more key figures in the story. At the time, Milner attended some lectures in Oxford given by Dana Scott. Dana Scott is another guy who got the Turing Award, and he got it for the invention of domain theory, amongst other things. He got it together with Michael Rabin, and we might hear about these guys in future seasons of this seminar series. He went to listen to these talks about domain theory, and he really thought that Dana Scott was getting at the heart of computation. So he began to be inspired. Remember, he was already interested in logic, but now things really started firing for him. Things started happening very fast. Now, logic, the relationship between computer science and logic, between machines and logic, between software and logic, it's a very interesting relationship. In Milner's words, you can have machines, remember theorem proving, you can have machines to prove theorems in logic. But then you can use logic to actually reason about the way the machines compute. Which means that you can actually machines to prove theorems in logic that have to do about the machines themselves. So the relationship is a very recursive one, if you wish. It's also an extremely rich one, and it sort of brings something fundamental about the connections between logic and the machines, computer science, the programs that run on the machines. So the next natural step was that Milner actually took a job where he could put all of these interests together. After talking to Zohar Manna during a trip to the US, he got a job at Mark Arthur's lab at Stanford in the AI laboratory, where, together with other people, he built an interactive proof of system called LCF. And this was an implementation of Dana Scott's, remember the guy I told you about before, Dana Scott's logic of computable functions, which was a logic that you can use to mechanize reasoning, which was amenable to computer assistance. Now, these are some of the people who he actually worked with at the time. Now, some of you might recognize the first name, Diffie. Diffie-Hellman, the algorithm for public key encryption. So this was before he interested in cryptography and became very famous for that. So it must have been one of his first jobs, programming LCF. Now, what they did was actually to create an interactive theorem prover. Note, not automated, interactive. What does this mean? This means that the machine does not prove the theorems always by itself, but it does so by interacting with the human user. That is to say, the human user can have an influence on how the machine assists him or her in proving a given theorem in the logic. The idea that the people behind LCF had was that since automated theorem prover was plateauing, there was more to be had by joining man and machine together to the greater good. Now, of course, we are talking about 1970. The computer technology at that time had serious drawbacks. For instance, you could not store in memory large proofs. Even today, there are theorems in mathematics, in informal mathematics, whose proof spans 10,000 pages. And this is human hand-wavy stuff. If you turn it into a formal proof, then most likely would be 1,000,000 pages. 1970. I remember my friends playing with Commodore 64 in the late 1980s or in the early 1980s. So there was not much memory available. You could not store so long proofs. The other thing was that the set of commands that you could use to tell the machine how to help you with the proofs was preset, essentially. And this leads to not very much flexibility in defining tactics, that is to say, sort of procedures, functions that you can use to tell the machine how they can help you with the proofs. So what Milner did was typical of his work. As soon as he had the system, he put it to work. And how did he put it to work? To verify the correctness of a compiler for a simple language. Now, the language that he considered was a very basic imperative language of the Algol family. It was essentially the while language that Anna and myself teach very often in the semantics course. It's very, very basic language. The target language was an assembly language for a machine with a stack-based language. And LCF, this system, is used to encode both the syntax and the semantics of the language, and to carry out a machine-assisted proof. In other words, what Milner and Weyrauch did in this 1972 paper was to prove the correctness first by hand, of the compiler by hand, and then to check their proof using the machine, using LCF, to be absolutely sure that the compiler generated correct target code for each input source language, source program. Now, this was seminal. Okay, the language was tiny, but nobody had done it before. Today, people do it for full-blown languages like nearly the whole of C. There is a compiler developed by Xavier Leroy and his friends, his colleagues at INRIA, that takes as input a large fragment of C, which is used for embedded systems application, and spits out PowerPC assembly code, and the compiler is formally verified using Coq, which is one of the grandchildren of LCF. So it's a matter of scale, of course, but the ideas are there. Now, Milner and his family decided to move back to the UK. They didn't want to raise their children in the US. And in his interview, he gives several reasons why he didn't want to do that. The first thing that they tried to do, together with these people, was to get rid of the drawbacks of Stanford LCS. Remember, you couldn't store all proofs. But why should you store proofs? Once you know that something is a theorem, you don't really care if you're a machine. You might care if you're a mathematician. But if you're a machine, you don't care how the proof works. Provided you've vetted it's a proof, the only thing you care about is the theorem that comes out at the end. So only store theorems. Second, you develop a full programming language that you can use to extend the set of commands that you can use to interact with the machine, with the proof assistant, to tell the proof assistant how to help you. And this programming language turned out to evolve into what is called ML, one of the archetypal functional programming languages. Remember the second complete and distinct contribution. Now, this is very powerful. Remember, before you had a predefined set of commands that were guaranteed to work, but you could not extend it. Now you have full liberty of extending the set of proof commands. With great power comes great responsibility. Major problem. Who prevents the user from asserting false theorems? As a proof command, you could say assert false. And then you have the most powerful proof system at your disposal. You can prove anything under the sky because false implies everything. Who allows you, prevents you from generating proof commands which are simply buggy? I mean, they use silly rules of inference. If it rains, then the floor is wet, or the pavement is wet. Since the pavement is wet, I conclude that it rained. That's not true, is it? But who prevents you from adding these rules of inference? The solution is, again, archetypal. Find a very simple way that prevents all this junk from happening. So what did Milner and his collaborators do? They did the following. They turned theorems into an abstract data type called THM for theorem. If something is type theorem, it's a theorem. It's guaranteed, no junk. Why? Because every time you have an abstract data type, you're all computer scientists in here, so I can afford to get into this. Every time you have an abstract data type, you need to construct elements of the data type using constructors. That's the only thing you can do with it. And the only constructors of the data type theorem are the rules of inference of the underlying logic. That is to say, you cannot cheat. So what is a consequence of this idea is the correctness of proofs is type checking in modern day computer language. Why? To know that something is a theorem is equivalent to saying that it is type theorem. If it has theorem THM, it's a theorem. Full stop. Beautiful solution, if you ask me. Now today, 40 years later, these things are out there and kicking. They've been used to verify all kinds of computing devices, including operating system kernels in Australia fairly recently. Properties of programming languages, their type systems. In mathematics, we had a guest speaker, Georges Gontier, who verified using Koch the four-color theorem. Recently, he verified the Phi-Thompson theorem in group theory, which was an even bigger achievement. And today, they are verifying, proof checking, the proof of the Kepler conjecture. That's the FlySpec project. So first summary, a first take-home thing, what Milner did with LCF has had a very rich lineage, and it's central to machine-assisted theorem proving today. Second contribution, programming language design and semantics. Here's a quote from when he received the honorary doctorate from the University of Bologna. He basically says, computers are incredibly versatile, but the versatility of computers is really essentially due to the versatility of the languages that we can use to communicate with them. The more languages, the better languages we have, the more we can do. And I can see Christian is nodding his head because now with Replicode is contributing to this versatility. And he said, the versatility of the languages appears to be unbounded. Well, at least it's at least bounded by our imagination, by our creativity. So what did Milner do for programming language design and implementation? Well, here are 3 quotes that essentially enucleate what was so cool and was still cool about ML. Remember, He needed a language to interact with theorem provers. He developed this language ML. As it turned out, this language, which was originally thought for interacting with theorem provers, was a full-blown programming language that you could use to do anything under the sky, not just interacting with theorem provers. It was a general-purpose functional programming language. The first quote mentions two key features: the escape mechanism, which today we know as exception handling, and programming with higher order functions, and the polymorphic type discipline. Now, polymorphism, that's a Greek-inspired word. Poly means many, morphs is forms. It's many forms. Objects, sort of entities in the programming language, can have many types. Now, when things have many types, you need to determine what type is the most applicable, what type is the most important, if any exists. And in fact, is there a type which is in some sense the mother of all types for that object? Also, how are you going to annotate your programs with types if if expressions in your programming language can have possibly unboundedly many types? Which one do you write down? What is the solution? You don't write down types. But then the system should actually infer them for you, because, as Milner says, types are the leaven of programming. They make it digestible. Programming without types is only for the super dupers amongst us. Most of us die when you try to do that. So these are the essential, I've already introduced the key features of the classic version of ML. Polymorphic type inference. You don't specify types, the system infers them for you. And objects can have multiple types. Escape mechanism, exceptions. That's what we call them today. If you think about theorem proving and telling theorem provers what to do, you want exceptions because they allow for backtracking. We all know that sometimes you try to prove something and you get stuck. What do? You backtrack. You're doing exception handling. Exception. The lemma I was trying to prove is false, so let me try to do something else. Or I cannot prove this lemma, let me prove something else. Higher order functions. That was important for his application, but in fact it's also useful in practice. Today, think of map reduce. What does map mean? Map means you have a sequence of objects and you want to apply a given function to each element in this sequence. That's the map function. And map reduce is just the Google paradigm for doing things particularly well. But it all comes from here. And it all requires the use of higher order functions. That is to say, functions that can take functions as inputs. So let me give you an example to make things very concrete. Actually, two examples. The first example is a specification of the length of a list function. It takes as input a list, and it tells you how long that list is. The first line says the length of an empty list is 0. If you have a non-empty list, then the length, this list is made of a first element followed by the follow-up list, and the length is 1 plus the length of the follow-up list. Note, pattern matching, a definition. But where are the types? There are no types. Why? Because the length function does not depend on the type of the element in the list. You don't want to define a length function for lists of integers, a length function for list of booleans, a length function for list of characters. Maybe you want to do that, but it would be overkill. It's redundant. But if you write something like that, then the system should tell you what type it is. And the ML type inference algorithm tells you that the type of the length expression is that it is a function that takes as input a list of elements of type A, but A is a variable over types. It's not a specific type, it's any type, and spits out an integer, which means that that expression there is syntactically correct. Because length works for lists of arbitrary type. So you can sum, you can apply length to a list of integers and a list of booleans. In fact, you can apply to a list of functions if you want. Second example, the map function. That's what I mentioned before. That's a function that takes two arguments. The first argument is a function. The second argument is a list. What is the idea? You map, sort of you apply f, the function f, to each one of the elements of the list. Now, what's the type of this thing? Well, the type inference algorithm for ML will tell you that map is a function that, given a function from elements of type A to elements of type B, and these are arbitrary types, and given a list of elements of type A, returns a list of elements of type B. A and B are not specific types. They can be any type. Now, how are these things inferred? Well, Milner proved one of the most important and influential theorems in the history of programming languages, at least according to Robert Harper. He showed that the type inference algorithm that he developed always terminates, and it always gives the most general type for any given expression. Now, what is the most general type? The most general type is a type that simply by instantiation allows you to derive all the types, all the other types for which the function you've defined makes sense. And so remember, the type of the length function was from a list, where A was unspecified, to int. A specific instance of this type is a list of integers to int, a list of booleans to int. These are all instances of this arbitrary expression, which is the most general one. Now, Andrew Appel, who's a programming language and security guy from Princeton, is a professor there, he says POPL, which is the Principles of Programming Languages Conference, if you're in programming languages, that's what you want to publish, is the principles of ML. That's a big thing to say. So basically, most of the things that people publish about, they are strongly related to what Milner did with ML. But that was not all. That's only about the types. Milner had ML. Remember, this is a language that he wanted to use to program theorem provers to do the things that he wanted to prove, to help him prove things. So it better be the case that this language is formally defined. There has to be a language definition. He asked himself, again, the philosophical question. What is a language? What constitutes a programming language? And his answer was, a programming language, whatever it is something that must be subject to rigorous study. The syntax must be formally specified, the semantics must be formally specified, otherwise we don't know what we are talking about. And why? Because you cannot do rigorous theory unless you have precise definitions. Precise definitions support implementation by ensuring compatibility. If you have a hand-wave definition of a programming language, you will get many hand-wave implementations, possibly incompatible ones. And we all know that they do exist. But if you have a precise definition of the language, that's the yardstick by which any implementation must be measured. And after many years, the definition of standard ML is the best example of a rigorous language definition for a fully grown, full-blown programming language. This was done by Robert Harper, whom I've already quoted a few times, Robin Milner, and Matt Stofte in at least 2 books. So how did they do it? Remember, Occam's razor. Things should be as simple as possible, but no simpler. Now, we're talking about a typed language, so what these 3 guys did was to give a precise description of the static semantics of the language, that is to say, associating to each program its type, and the dynamic semantics, associating to each program, given an input, the result that emerges from the computation of that program, if any. Now, this result can be either a proper answer, like 35, or a specific symbol, a constant, called wrong. which means that something really bad happened in your program. Now, how do we know that the language, that the programs that you can write in ML behave well? This is enucleated, this is represented in a nutshell by a theorem that Milner, Harper, and Matstofte proved, and they call the type safety theorem. In a nutshell, this theorem says that if you have a program and the ML compiler, type inference algorithm, tells you this program is well typed, it will never go wrong when it's run. Well-typed programs do not go wrong. More technically, this means that if the inference system for ML, which is rule-based, tells you that the program is a given type, and it also tells you that the program yields a given result, then the result is a value of the right type. So if the program is type integer, the result is an integer. If the program is of type Boolean, the result is a Boolean. In other words, well-typed programs do not actually go wrong at runtime. For how many languages can you guarantee that? Well, I don't know. In this case, for ML, you're sure. So some people say that this theorem is the curse of programming language semantics people, because it's very, very difficult to improve, to do significantly better. So if you want to publish type safety theorems, you need to do really a lot of work. This was already published, so you cannot republish it. Now on to the third contribution, which is the one which is closest to my heart, of course. That's concurrency. Now, again, let me bring you back to one of the red threads in Milner's work. Already in the world of theorem provers, he moved from automated theorem proving to interactive theorem proving. So interaction for him was of interest already then. In fact, he already started thinking about interaction and concurrency when he was at Stanford working on LCF. He published a paper on concurrency already in 1973. He doesn't remember how he actually got interested in concurrency, he says himself, but he really wondered at a certain point what would happen if you took automata, good old-fashioned automata that you all know and love, and you made them interact one with the other. That's the essence of parallelism, communication, interaction. He said, okay, I was really interested in this theorem proving stuff, but I don't think it was getting at the heart of computation. What Dana Scott was doing in domain theory was getting at the heart of computation. I wanted to do so. And I felt that concurrency, the notion of interactive automata, would shed light on computation. Because his philosophical position slowly turned into the case that computation is actually a special case of communication. So if you know how to handle communication, you know how to describe arbitrary computation. So his goal was to seek communication primitives that underlie computing, not have communication primitives to somehow improve computing. For him, the communication primitives were at the heart of computing from the beginning. Of course, eventually, I mean, these communication primitives should also be reasonable from an engineering viewpoint, and he was very interested in that because he was always engineering systems, as well as developing theories about them. So the type of communication primitive that he hit upon was handshake communication, which was channel-based. Now, the channel, you can think of it as an abstraction of a communication medium. Okay, like maybe a telephone number. But it's a telephone number that maybe only two people share, you and me. And we can use it to communicate one with the other. It's a bidirectional telephone number or a little wire. No shared memory whatsoever. Message passing. Remember, Occam's razor. Now, people might say, shit, I mean, in all computing that we know, there are variables lying around. There are active objects, the programs that operate on passive objects, the variables, the memory. But why should there be this distinction? You can view any piece of memory as a process in itself. A variable is actually an active computational object, or can be viewed as an active computational object that is willing to communicate with its environment by letting its environment read its value or write a new value. So everything can be viewed as a process. And Milner developed a toy language, if you wish, called Calculus of Communicating Systems, CCS, which could be used to express parallel processes communicating by means of handshake communication. One sender, one receiver who handshake and exchange data in the process, possibly. Okay, for those who have followed the courses by Anne and myself, or have read our book, they might recognize this little description, piece of syntax that you have over there. This describes a very small university, even smaller than ours, which has one coffee machine and one computer scientist running in parallel one with the other and communicating by exchanging coins and cups of coffee. The computer scientist interacts with the outside environment to the university by outputting publications on the publication port, pub. That's how you read this stuff. And moreover, the coin and the coffee ports are only known to the computer scientist and the coffee machine, so they are not known to anyone outside the university. Now, these are essentially, apart from two, these are essentially all the constructs that you have in CCS, nothing more. So it's a really toy language. However, it can express a lot. Now, this theory has a really, really rich lineage. I'm not going to tell you about the technicalities. I mean, you can read them elsewhere, or you can ask about them when you have time, or you can take our courses. You can do whatever you like. You can buy our book. You can do whatever you like. Or you can read Milner's book so that you get the theory from the horse's mouth. However, I read the first two books that I mentioned before, the ones with the highest number of citations, there were two books on CCS. Together, they have over more than 14,000 citations, or thereabouts. Our former supervisor, Matthew Hennessy, who worked for many years with Milner, when he was here to give a talk, he had a quote. I mean, this is a quote from a rough quotation from what he said. He said, "Every 5 years I tell myself, this is the last paper in which I build on CCS, and then I write another one." This stuff keeps having influence. But did Milner stop there? No, he was always looking for new challenges. What was the next challenge? The next challenge was mobile computing. And that's what he worked on from roughly around 1987 until he passed away in 2010. Basically, he said, okay, sort of, what can you do in CCS? Along communication channels, you can pass data. But you cannot pass the communication channels themselves. Let me continue with the analogy of the telephone numbers. Now, you can think of a telephone number as a communication channel. I can use that channel to talk to any of you, provided you have the telephone number, and the data I transfer is what I tell you, possibly, in my conversation. Now, if in my conversation, I pass to you a telephone number, then I give you a channel that you can use to communicate with whoever has that telephone number. That was disallowed in CCS. And Milner was aware that this was a limitation, but he said, okay, I think it was a good idea to focus on something more basic first, because passing communication channels, passing pointers, if you wish, is hard. It's difficult to understand. No surprise people have trouble with pointers, because they are tricky. And in this case, we are passing communication pointers, if you wish. However, in 1987, he said, okay, he thought, the time is ripe. We got to do this. What did he do? He essentially added to the old CCS that he had in his hands, and that he knew and loved for sure, two simple things. First of all, you remove the restriction that you cannot pass communication channels in communication. Now you can send telephone numbers. by continuing with my analogy. Second, you do something which is called technically scope extrusion. Now, that's abstruse, isn't it? But it means something really simple, even though it's difficult to get it right formally. Now, let me continue with the analogy of the telephone number. Some people have secret telephone numbers. They are not listed anywhere. Okay? But if you and I know a secret telephone number, we can call the person who has it. Maybe that person has given it to us. But that telephone number is only known possibly to the three of us. The two who know it and the person who has it. The scope, that's computer science speech, if you wish, or jargon, the scope of the telephone number is three people. But if I send that secret telephone number to someone else, now the scope of the telephone number is enlarged. Now it's four of us who know it. So by sending secret things to someone, we enlarge the scope of the secret thing so that more people know it. This is what scope extrusion means. You enlarge the scope of this secret thing. Note, sometimes when you think about mobile computing, you think about actual programs running. For instance, we get a whole program update for our operating system. That's a piece of code that migrates and is run on our machine. In CCS, you cannot do that. You can only pass communication channels, not whole pieces of code. Is this a limitation? It turns out it isn't, because you can simulate code motion by using simple communication channel motion, or if you wish, pointer motion. So again, Occam's razor work. As simple as possible, but no simpler. Now, the legacy of this thing is still ongoing. People are beavering away on these ideas as we speak, literally, and it has had a lot of impact, even in biology. There are applications to molecular biology. People model biological reactions using the pi calculus, which is this calculus CCS plus mobility. You can model business processes. There are new programming languages, like one called Scribble, that has been developed, amongst others, by Kohei Honda, who passed away, unfortunately, very recently. It's used to model, of course, mobile devices and all that stuff. But Milner didn't stop there. During his last days, he was still working on a further improvement on that model, which is called bigraphs, developing the foundations for ubiquitous computing. This was basically meant to replace the von Neumann architecture, von Neumann type abstract machines, but for ubiquitous computing. So let me sum up by trying to draw some conclusion as to what we can learn from Robin Milner. Well, in his work, I think you can see very clearly that he had this philosophical viewpoint, which in a way was one of his strong points, and that sort of was a guiding light throughout his work. For him, computer science has both a theoretical and a practical aspect. The theoretical aspect provides the mathematical models that ease the construction of systems. And computing systems provide the experimental side, and the two feed on one another. Look at this quote. He says, we are trying to find foundations, but we should always be open to new applications that give rise to new foundations. And as you can see, that's something he did at least 4 times in his career. He wants people eventually to be able to talk about computational processes in the same way as we are taught about functions in mathematics. And that's a quite telling game. I'm not interested in short-term gains. Most of us are, because what we look for is our next publication. That's, if you wish, a short-term game. But he was interested in the big gains. Of course, he could afford to do that. I can't. But he also has some lessons for everyday academic life, but not only. Throughout his career, he was very thorough. You should develop, whatever you do, you should develop craftsmanship. And whatever you do, Be a careful expositor of what your ideas are. Make your research accessible to students and practitioners. Write books. Remember, 4 of his top 6 most cited publications are books. He even wrote a book about the biographical model as he was developing. This was published just the year he died. So he wrote books up to this very end. And those, of course, it didn't have enough time to become widely cited, but most likely will. So his citation count is likely to go up. Seek challenges and freshness of thought. He sought new challenges all the time, from theorem proving to programming language. How do you make a good programming language design? What is a good language for programming? Concurrency, mobility, ubiquitous computing. And I think only death stopped him. But I stopped before. Thank you.
I have a question which relates maybe to a later talk. You said you studied relational algebra for